Hi, everybody. My name is Maxime, and today I'm going to be telling you about optimizing YJIT's performance from inception to production. So, thank you. I mean, wait until after the talk to applaud. Just kidding. So we all love Ruby, but optimizing Ruby's performance has proven to be sometimes a difficult and scary problem. There have been many different projects trying to build just-in-time compilers for Ruby to improve its performance. But most of these projects today are abandoned or maybe didn't reach the outcome that they hoped at the beginning in terms of adoption. But recently, YJIT has reached an important milestone at Shopify. We have deemed it to be quote-unquote production ready. And it's not just talk. We've deployed YJIT to all of the StoreFront renderer infrastructure at Shopify, serving all of the requests at Shopify Store. So every time you go to a Shopify Store, you're using code that was run by YJIT. And we're seeing really nice end-to-end speedups. And it's not just us. As of yesterday, Discourse has announced that they are also using YJIT in productions and getting similar speedups as well. So this talk is not just technical. It's about some of the decisions that have been made that led to YJIT being production ready. I also want to talk a little bit about the origin story, the background behind YJIT, where it came from, where it started, because, well, there's a famous quote by Mary Kay Ash: "Ideas are a dime a dozen. People who implement them are priceless." And I think when you read the full quotes, at least what I get from it is that there are many good ideas out there, but there aren't enough people implementing these good ideas. Unfortunately, people tend to shorten the quote like this: "Ideas are a dime a dozen." You hear that all the time. And I think you can have a very cynical and dismissive misinterpretation, which is that all ideas are equally worthwhile or worth less. It's just a matter of implementation. You could take any idea. If you just throw enough resources and manpower at it, you'll make it work. But unfortunately, I think that's not true. I think that if you start from a bad concept, you may never get the outcome that you want, no matter how many billions or trillions of dollars or thousands of human years you throw at the problem. So in this talk, I want to talk a little bit about what is YJIT, where it came from, YJIT Bench, which is the benchmark suite that we've been curating to evaluate YJIT's performance, the data-driven approach that we take to optimization, how we evaluate YJIT's performance on a real production workload, some of the engineering trade-offs that are involved in JIT compiler design, and also reducing YJIT's memory overhead and future optimization work. So YJIT is a project that was started over 2 years ago to build a new JIT compiler for Ruby. It was built primarily at Shopify, but fully open source, BSD. But we've also had some significant contributions from folks at GitHub. One key aspect of this project is that we take a data-driven approach to optimization. To do that, we have a large and diverse set of benchmarks. We benchmark often, and we gathered detailed metrics. So YJIT is a team effort. It's not just me. It's much bigger than just one person, and this project would not be where it is today without the contribution of many amazing folks, amazing programmers that I'm lucky enough to work with. Some of the original goals of the YJIT project were to be able to run any Ruby code, be 100% compatible with what we run in production at Shopify. We couldn't really have it any other way because the code bases that we run at Shopify are just so huge that it just seemed impossible to ask our developers to change the code base to fit the JIT, so to speak. We also wanted to reach double-digit speedups on real-world software. Our primary focus is web workloads at Shopify, so that means like mostly Ruby on Rails and similar code. As much as possible, from the start, we also wanted to make sure YJIT never slows Ruby code down. Worst case, no speed up, but no slowdown either. We'll touch on this again later. Might not seem obvious, like how could a JIT compiler actually slow things down? well, it can happen. And we also wanted YJIT to be well tested and stable. Ruby's very large test suite has been very helpful in this. In terms of features, YJIT does lazy generation of machine code. It does an efficient linearization of machine code so that it works well with the instruction caches, runtime value promotion, type-based specialization, speculative optimization and de-optimization, and it has polymorphic inline caches, not just for call sites, but also for setIvar and getIvar. But there's more. In the last year, we've put a lot of work into YJIT for Ruby 3.2. We ported YJIT to Rust, which was originally unplanned. We implemented a new backend for ARM64, which gives us native support for Apple hardware and Raspberry Pi, and with good performance too, actually even sometimes better performance than an x86. Finer grained constant cache invalidation, many performance optimizations. We've improved YJIT's memory usage, which is a key part in making it quote-unquote production ready. We've added support for object shapes in YJIT, also for variable with allocation. And also at the end of 2022, we deployed YJIT worldwide on our SFR infrastructure and deemed it no longer experimental. I don't know about you, but I was really happy with this long list. So yeah, let's go back a little bit to the origin of YJIT and how it started, at least from my perspective. I started an undergraduate degree at McGill University in Montreal, Canada in 2004. And I discovered a love and passion for compilers. In 2007, I joined the team of Professor Laurie Hendren at McGill University's Stable Lab to do a master's degree. And my advisor wanted me to work on a JIT compiler for MATLAB. I think, well, MATLAB is a language that does numerical computations, so I think what she had in mind was that I would focus on numerical optimizations, so optimizing like matrix multiplications and all kinds of operations that you can do on matrices. But while I was working on this, I had a realization, because MATLAB was kind of like my first real exposure to dynamically typed programming languages. MATLAB is dynamically typed, kind of like Ruby. And I realized that there was a lot of things that we could do in terms of like type optimizations. Because if you want to optimize, say, matrix multiplications, first you have to know that the things that you're multiplying are actually matrices and that they're not like Boolean values or integers, for example. So the focus of my master's was on generating specialized versions of MATLAB functions based on the arguments and type propagation, and culminated in publishing a paper about this technique. Then in 2009, I went over the hill in Montreal. Like both our two biggest universities are on top of the mountain at the center of the city. So I just crossed over the hill to University of Montreal and joined Mark Feely's lab in 2009 for a PhD. My original plan, what I really wanted to do at the start was to optimize Python with what's called a hybrid type analysis. We actually ended up focusing on optimizing JavaScript with what's called a hybrid type analysis. So hybrid type analysis is a mix of an procedural type analysis with some speculative de-optimization. So traditional fixed point type analyses that are used in the world of ahead of time compilers can be fairly expensive, and they tend not to work with dynamically typed languages because things like eval tend to get in the way. For a language like Ruby or JavaScript or Python, basically you can load new code at any time, and so you run into a problem where if you load all of the source code that you have for your program and you do a type analysis of this program to try to determine the types of all the variables, but then suddenly inside of an if statement, someone loads a new module into the program. That new module can come and it can change the types of your variables, and it can break all of the assumptions that you've made about your program, which render the results of your type analysis invalid. So there's kind of like a research question of how do you get around this problem? And the approach that I wanted to take was to have an analysis that would speculate that the results that we have are correct, And then if we contradict those assumptions, we throw away the code, basically, we throw away parts of the code, invalidate those assumptions, rerun the type analysis. And I was convinced that this would work. My advisor was skeptical. I worked hard on it for 2 years, but unfortunately, I got scooped, which is about the worst thing that can happen when you do a PhD. So some researchers that were working at Mozilla Corporation published basically exactly what I wanted to do for my PhD. They made it work inside of the SpiderMonkey JIT. And to be honest, they did a better job than I would have because they had multiple people helping them, working on the SpiderMonkey team, corporate resources. And so I was kind of having an existential crisis for a little bit because someone basically did my PhD better than I would have. So what was I going to do? So I did a little bit of soul searching, and after that, my advisor and I tried to look at the problem from a different approach, basically. Could we do type specializations of programs without doing a type analysis? Traditional type analysis, they use a lot of memory and time, and they have potentially bad asymptotic behavior in the worst cases. And using what's called a hybrid type analysis means that when you break your type assumptions, you end up having to throw away a lot of code, and you have to use this technique called on-stack replacement to de-optimize. That can be very expensive, and having spoken to researchers at Mozilla, this turned out to be the Achilles heel of this technique. They implemented it in SpiderMonkey, and shortly after, they ended up yanking it out because it was doing too much de-optimization, and it wasn't worth it. So could we specialize the types in a program without type analysis? Well, I think we ended up finding something that was simpler, faster, and also more precise. But how? Well, let's go back to the fundamentals a little bit and ask the question, what is a just-in-time compiler? I think many people, when they think of just-in-time compilers, they think, well, it's like a static ahead-of-time compiler, but it runs just when you start the program. And at the most basic level, the most basic JIT compiler could be like that, but it can be a lot more than that as well. And I think the question I wanted to ask myself during my PhD is, what is the biggest fundamental advantage that a JIT compiler has that an ahead-of-time static compiler does not? And I think this advantage comes in the form of what can a JIT compiler do that an ahead-of-time compiler can't? And it's that a JIT compiler can observe the program as it runs. A JIT compiler can know everything about the running program. Like, you literally have access to the program while it's running. You can look at the types of all of the variables inside the program. You can see which way every branch goes in the program as it's executing. If you had a hash map in memory inside of a JIT compiler, you could know all of the fields inside the hash map. So you have so much more data. There has to be a way to use this data to generate code that's more efficient than you could if you're just looking statically at the program and you don't know very much except just the types. So now that we have this deep insight, what can we actually do with it? Well, maybe we can reimagine how a JIT compiler works and let the running program kind of drive its own optimization. And so the technique that we devised during my PhD is called lazy basic block versioning. And it works by unfolding the control flow graph. So we leverage the power of self-modifying code to do tail duplication or tail splitting and propagate type information. So we generate code not just when the program starts, but as late as possible. And by generating code as late as possible, we make sure that we can accumulate as much information as possible. We have as much information as we possibly can when we're about to generate that machine code. This technique, we tried to publish it, but it originally wasn't super well received in the compiler community. I think it was maybe too different from what existed out there. And so we tried to publish a paper about it. I thought it was a very good paper. We had lots of benchmarks. We had lots of very good results. But the paper was rejected 3 times. And every time the paper was rejected, I cried, because I spent 6 months of my life working really, really hard on this idea. I was convinced I had a really good paper, but it got rejected. Thankfully, on the 4th try, we did get it into eCoop. And we also published after that a follow-up paper where we extended the technique entered procedurally, and we added notably typed object shapes. This is one of my favorite graphs from our second paper about basic block versioning. It's not super easy to make sense of, but basically, one of the things I wanted to do in our second paper was to compare the effectiveness of lazy basic block versioning versus a traditional type analysis. And I wanted to measure how effective it was in terms of the percentage of dynamic type checks in the program that we're able to eliminate with basic block versioning versus with a traditional fixed point type analysis. So in this graph, higher is better. And one of the problems that I had was that I wanted to compare basic block versioning versus a traditional type analysis, but there's a question of like, which type analysis am I going to compare my technique against? Because the type analysis is like its own entire field. There are researchers that have dedicated their entire life to this. And so I can't just compare one type analysis or like which one am I going to implement. And if I implement a technique and I make a mistake, I'm not doing a fair comparison. And if I implement a technique that's not quote unquote state of the art, maybe the reviewers will tell me, well, you didn't compare your technique against the state of the art, so maybe your stuff's not good enough. So the approach that I decided to take, well, is to get an upper bound. What is the maximum performance that a type analysis could possibly hope to get? So I ran all of the benchmarks, and I recorded the way that each dynamic type test goes inside all of the benchmarks. And I said, well, the best that a type analysis could hope to do is that if the type check always goes the same way, we say that an optimal type analysis could eliminate it. And so that gives me an upper bound on how well the most perfect type analysis with perfect information could possibly hope to do. And what this graph shows is that on average, with basic block versioning, we were able to do better than that. We were able to eliminate more than the best possible result that you could possibly get with a fixed point type analysis. So you might be asking yourself, well, how is that even possible? Well, the secret sauce is that basic block versioning is able to do tail splitting. So some of these type checks that don't always go the same way, it's able to split them in two and generate like two parallel code paths, basically. And by doing that, then we can eliminate more type checks at runtime. Okay, so how does that relate to Shopify and Ruby and everything else? Well, shortly after joining Shopify, I discussed with Rafael Franca, which was my manager at the time, the idea of building a toy JIT in CRuby. My manager thought maybe it was interesting. I wasn't really sure if I wanted to jump into this project because it seemed big and scary, but I met Aaron Patterson and Alan Wu. I remember discussing this idea with Aaron Patterson, and I thought, well, do you think we could build a JIT in CRuby? And Alan and Aaron immediately said, I'm in. I want to be part of this project. And so that got me excited because I thought, if I'm not alone, then maybe we can actually make this work. And so I convinced Shopify to give us 3 months to build kind of a prototype with the idea that we would demonstrate we can get some speedups on small benchmarks, and if we can do that, maybe they would let us work on a bigger project. So the way that this works, Alan gave a keynote about it last year, but the way that the first prototype MicroJIT worked is basically if for some common sequences of YARV instructions, we can generate basically like super instructions where we merge the instructions together. We eliminate the dispatch overhead and we do a few optimizations, but only for like linear sequences of code. And the outcome of this was that we got up to 10% speedups on some of the smaller benchmarks, but it actually underperformed on Rails bench. It actually slowed things down a little bit. So it was like a little bit of a mixed success, but I think the positive thing is we managed to convince Shopify that we actually knew what we were doing and that they were willing to invest a little bit more into this. So for our second attempt, we started working on YJIT. YJIT was going to be not a toy JIT anymore, it was going to leverage the full power of lazy basic block versioning. For simplicity, at first we wanted to target only x86-64, and we had 9 months to deliver double-digit speedups on opt-caret and single-digit speedups on Rails bench. all at the same time maintaining quick warm-up times and delivering speedups in less than 30 seconds. So those were the original goals of the project. And at the end of the day, we had better success than expected. We managed to deliver clear double-digit speedups on some realistic benchmarks, sometimes over 20%. And we managed to also run the code that Shopify uses for StoreFront renderer. And so to show that YJIT has real potential after even less than 9 months. And then that's how we got an invitation to upstream YJIT into CRuby. So let's talk a little bit about benchmarking. So I think when working on a JIT compiler or, well, any kind of software engineering project, benchmarking is crucial. Historically, there's been kind of a focus on opcaret and micro benchmarks when optimizing CRuby. And this seemed like a problem because opcaret isn't necessarily representative of most Ruby code. I think opcaret is cool, right? NES emulators are fun. But most of the people using Ruby out there are not actually using NES emulators. And one of the problems with micro benchmarks or with benchmarks like opcaret is that a lot of the time they only test the easy case. So for example, when people write simple benchmarks, usually there's no inline cache misses. So you're only testing the fast path, which is kind of an idealist case. So the benchmarks written by CRuby devs are benchmarks that make us look good. But that's not necessarily what we want. Like, we want the truth. So the choice of benchmarks really matters. Compilers are really complex. There's a lot of different things that you could do, that you could optimize. And so there's a kind of a question of like, what type of workload are you going to choose to focus on? I think you want to know where you don't perform well, right? You want to know what are like the pathological cases that you're going to encounter in practice. And you want to be honest with yourself. And yeah, when I say honest with yourself, that means ideally not benchmarks written by you. So we started working on YJIT Bench, which was a suite of benchmarks that we were going to use for benchmarking YJIT. My initial hope with YJIT Bench was that each developer who's working on YJIT should be able to run benchmarks pretty easily. I wanted to make the setup process easy. I think one of the worst things for an open source project is when you go to the GitHub page and there's a long list of instructions that you have to do to set up the program, right? If you go to a GitHub page or something and there's like 10 or 20 steps to get the program to run, chances are you're gonna be like, oh, well, is there something else I could use, right? You're not gonna do it. Like, people are lazy, and I include myself in that. So I wanted to have something that was super easy to install, minimal steps to encourage people working on YJIT to, including myself, to run experiments often, make it as foolproof as possible. Just type one command in your shell, get the results in 10 to 30 minutes. And I want us to have like a good, high-quality set of curated benchmarks. And so running YJIT Bench can be pretty simple, right? You clone the repo, and then there's a script that /run benchmarks.rb. By default, it does something sensible even if you don't provide any command line arguments. And in YJIT Bench, we have 3 different categories of benchmarks. We have what we call headline benchmarks. Headline benchmarks are the benchmarks that we want to focus most of our attention on. They're based on real, widely used gems that we didn't write ourselves, right? So that we know we're not cheating. We try to be representative of real workloads. For us at Shopify, that means that there's a heavier emphasis on web workloads and things that we use at Shopify. But we also have micro benchmarks. I think micro benchmarks are still useful. Like, I think if you write on a compiler project, you should try to have big, realistic benchmarks. But micro benchmarks are still useful to diagnose performance bugs sometimes. And we also have a category called other benchmarks, which are smaller synthetic benchmarks, which can sometimes be interesting data points. And that includes benchmarks from like the language shootout and also opcaret. So yes, we still do benchmark on opcaret. And in this set of benchmarks, we also have kind of a progression which has allowed us to level up over time. So when we started working on YJIT, on MicroJIT, before there was YJIT, we looked at micro benchmarks. And then we got to a point where we were able to show speedups on micro benchmarks. And then afterwards, we started working on UpCaret. And at first, we were not faster on UpCaret. It actually took us like 2-3 months to become faster on UpCaret. And once we got to that point, we moved on to Shopify's liquid template rendering. And it took a little while, but then we got like a few percent speed up. And then the bigger beast was RailsBench. And then that took several more months for us to eventually become faster on RailsBench. And then eventually, we moved to actually deploying in production. Benchmarks are not the only thing that matters. There's also a methodology to benchmarking. I like to tell people, like, avoid benchmarking on your laptop if possible. A lot of the times, it's just tempting. Hey, it's right here. I want to run the benchmarks on my laptop. Sometimes that's fine, but sometimes it's not. So we recommend, if possible, benchmarking on single-tenant bare metal instances on dedicated servers. We try to do that if possible. And we try to stabilize the benchmark results as much as possible. What do I mean by stabilizing the benchmark results? Well, modern CPUs have this thing called turbo boost. So when you run a program and it's very demanding, it's going to ramp up the clock speed of your CPU as high as possible for as long as possible. The problem with that is that the temperature of your CPU is like hidden state that you don't have control over. So how long your CPU can stay at the maximum clock speed is going to depend on factors like the weather outside. So it doesn't make for very repeatable benchmarking. So ideally, what we want is to stabilize things as much as possible so that our results are repeatable over time. And so how do we do that? Well, in Linux, when working on Intel machines, you can change variables associated with Intel P state to disable turbo boost. When you disable turbo boost, you don't want to stay in the maximum boosted configuration. You actually want to stay at the lower base frequency because your CPU cannot stay at the maximum boost for very long. We disable address space layout randomization because that introduces non-determinism in benchmarking. And we also try to pin the process to one single core when benchmarking YJIT. This is to minimize cache effects because different CPU cores have their own L1 caches, which are going to have a different state. So ideally, you want the processor to remain on the same core. And if you do all of these things, it works. You really do get much more stable benchmarking results across time. So let's talk a little bit about the evolution of YJIT's performance over time. I went back in time a little bit, and I benchmarked Ruby 3.1, 3.2, and 3.3 with and without YJIT on some of our headline benchmarks. And as we can see, there's been a progression and improvement in the performance of the interpreter over time, but enabling YJIT on those benchmarks actually makes a really striking difference. For example, for active record, we're now more than 2 times faster than Ruby 3.1 without YJIT. And if we look at everyone's favorite benchmark, UpCaret, the performance improvement over time is even more striking. As we can see with Ruby 3.3 plus YJIT, we're almost 3 times faster than Ruby 2.7 without YJIT, so we're almost at Ruby 3x3. And I think by the end of the year, we should actually be able to cross the 3x barrier. Okay, let's talk about metrics. So there's a quote by Peter Drucker that says, "You can't improve what you don't measure." Peter Drucker was not a compiler engineer, he was a business guy, but I think this quote also matters a lot in the world of compilers. It's important to have good metrics. So why do you want good metrics? Well, benchmarking measurements are noisy. There's a noise threshold of about 1 to 2%. And basically, some optimizations have no visible effect on performance, I should say, because sometimes the delta is too small. You make a small change in your compiler, you generate slightly better machine code, you rerun your benchmark. You don't actually see any performance improvement. What do you do if you can't test your change? Well, you have to use different metrics. So for example, you could look at the number of instructions executed, you could look at the size of the machine code you generate, and just believe that if you generate smaller machine code, things will get faster over time, which they tend to do. In YJIT, we also look at the number of side exits. We want to increase the percentage of time that is spent in machine code generated by YJIT as opposed to code that is executed by the interpreter. So basically, benchmarks tell you how fast you are, but they don't necessarily tell you what to optimize. And so Ruby is a complex language. Every operation in Ruby applies to multiple types. It's important for us to gather useful metrics to guide development to kind of decide what should we optimize among all of the possible things that we could optimize, because otherwise we're kind of operating on intuition. And I know everyone likes to think, well, human intuition can be wrong, but my intuition is actually right most of the time, right? Because I'm a good engineer. But it's still nice to have data, right? It's nice to make decisions based on data. So relatively early in YJIT's development, we added a command line option called --YJIT stats, which dumps a bunch of useful statistics. And our main concern, like I said, was maximizing the time spent in JIT code. So we have a script in YJIT bench to run a benchmark one time. We can run it with --YJIT stats. For example, with a Rails bench, then the benchmark runs for a little while. Once it's done running, it dumps a bunch of numbers. Most importantly, one of the main numbers that we look at is what we call the ratio in YJIT. So we can compute the percentage of the ARV instructions that are executed by code generated by YJIT versus by the interpreter. And we want that number to be as high as possible because there's a lot of overhead in switching between the interpreter and YJIT code. We also track which ARV instructions cause us to exit to the interpreter the most often, and we rank them by frequency. And you can plot that on a pie chart because everyone loves pie charts. And we see like most of the time it's the send instruction that causes us to exit to the interpreter. So maybe we should focus some effort on the send instruction next, and we can drill down deeper into like which specific reasons cause the send instruction to exit to the interpreter. For example, maybe something we don't handle about block arguments that we should look at. Okay, let's talk about StoreFront renderer and our production deployments. So Shopify StoreFront renderer is the infrastructure for rendering all of the Shopify stores to our customers. It gets executed every time you visit a Shopify store. It's mostly written in Ruby. It depends on over 220 Ruby gems. It powers over 4.5 million e-commerce sites. And it's used by sellers in over 175 countries. I can't publicly state how many servers of CPU core that is, but I can disclose that there's multiple large data centers or multiple large clusters that are distributed across the world. Our infrastructure is capable of serving over 75 million requests per minute or 3 terabytes per minute of traffic. It serves up to 1.27 million requests per second, and in 2022, it's processed over $197 billion of transaction volume. We want to know how fast YJIT is while running SFR. One of the challenges that we face with that is that the traffic that StoreFront renderer gets is going to vary based on the region of the world, the time of day, and world events. What do I mean by that? Well, the naive approach that people tend to want to take when they benchmark a change in production is like, I'm going to look at the performance, how long it takes to generate the web request before, and then I'm going to deploy my commit, and I'll look at the time it takes to generate the web requests after, and I'll compare the before and after, and I'll know how fast that is. That's no good. That's not good at all. Why? Because, well, maybe in America, after 6 p.m. people get home and they go shopping. So the web traffic that you get before 6 p.m. and after 6 p.m. is not the same. And in Australia, people are in a different time zone, so they don't follow the same patterns. Not only that, people in America and Australia and Japan, they visit different stores, they buy different merchandise. So you can't just compare random values and get a fair assessment. So you have to have proper experimental design. So that means like a separation of test and control. For for benchmarking YJIT in production, what we do is that in each of our global clusters, we have test, control, and stats machines that all run the same Ruby commit. And so basically, we can measure the time it takes to render traffic with YJIT and without YJIT in all of the different parts of the world at the same time. And we also have different stats machines that gather YJIT stats. And the reason we have different stats machines as well is because of the Heisenberg uncertainty principles, so to speak. So gathering YJIT stats requires us to generate different machine code, and so it affects the performance. And so to gather those stats, we need a different configuration because otherwise it would pollute the rest of our numbers. In January 2023, we were getting something like 6% speed up end-to-end on the average request time on StoreFront renderer. More recently, we switched to a different dashboard software that looks different, but now we're up to 18% end-to-end speedups. So that includes also all of the time that is needed to access databases in order to generate requests. But that 18% is very meaningful because it can mean a lot of money in server infrastructure every year. We also measure, like I said, YJIT stats on StoreFront renderer, so we can know like which YARV instructions cause us to exit to the interpreter the most often. We can again like drill down more specific reasons for send, for example. Okay, for the next section, I want to talk a little bit about just-in-time compiler trade-offs. Engineering is all about trade-offs, right? You've all seen like those triangles. You can only have 2 out of 3. JIT compiler design is multifaceted. Like I said earlier, a good JIT compiler is not just an ahead-of-time compiler that runs when you start your program. You have to juggle multiple trade-offs. There's the performance of the generated code, but there's also how long it takes for the JIT compiler to generate code. Because the JIT compiler runs at the same time as your program, if it takes too long to generate code, you could actually slow your program down. And there's also the question of memory overhead. So JIT compilers need memory to do what they do. If you use too much memory, then maybe that's not good, because if you have a bunch of processes running on your server, at some point you're going to max out your memory, and you're not going to be able to run as many processes. So a JIT compiler has to invest memory and time into generating faster code. It's an investment thing, right? So the JIT compiler has to pay for itself. And that's a careful balancing act, so to speak. But we get access, we get access to privileged information about a running program. We can observe it while it runs, and we can use that to guide the trade-offs that we make. So compiling code takes time. The JIT compiler has to be able to compile fast enough to pay for itself. We have to make sure that YJIT generates code fast. And to do that, we avoid doing long analyses. We avoid dynamic memory allocations as much as possible, or we at least try to minimize them. We try to minimize the number of optimization passes that we do in YJIT as well. And there's also a question of what we call amortization. So a JIT compiler has to pay for itself. The worst thing that you could do in a JIT compiler is to spend a bunch of time compiling code that's only going to be run once. For example, all of the code that runs at initialization time when you load your Ruby program, code that just sets a bunch of global variables that only runs one time, you probably don't want to JIT compile that code at all. You should run it in the interpreter, because if the time that you spend generating machine code would be slower than the time it would take the interpreter to run that code that's only going to get run once. So we use a really simple strategy in YJIT, which is like we have we call it a call threshold, basically. So we only JIT compile methods when they run a certain number of times. This threshold is tunable, and the higher you set it, basically, the more you need to call a method a certain number of times before we generate JIT code. It's a really simple strategy, but we found it works really well. For StoreFront renderer, we set it to something like 1,000, and that avoids like immediately JITting a bunch of code when we start up the process. which is important because people at Shopify will deploy code sometimes like every 15 minutes. JIT compilers also add memory overhead. There's the generated machine code, but as Alan was saying earlier, JIT compilers actually spend a bunch of memory to store metadata, which is just meta information associated with the generated code. So that metadata is things like type information, GC information, information that we need to de-optimize. The metric we look at the most is the resident set size, which you can measure with the PS command on Linux. Recently, we also added a graph that tracks on speed.yjit.org how much memory is used by each benchmark with YJIT and without YJIT, so that you can see how much memory overhead YJIT adds. It used to be a lot. It used to be really, really bad in Ruby 3.1, but for Ruby 3.2, we've made some big improvements. The biggest improvement that has been made is actually something that Alan Wu did. He added a lazy memory allocation strategy. So instead of allocating a really large piece of machine code as soon as YJIT starts, we do this lazily and we map pages from executable memory as needed. So when YJIT is started, we do a call to mmap to reserve a chunk of address space where we're going to write the machine code. But we mark it as prot none, which means that the pages can't be accessed. So wait, what does that mean? Like, we're telling the operating system we want a large chunk of memory, but basically we can't touch it. We're not going to touch it. So it just means like we want to reserve this address space so that the operating system is not going to put anything else in there because we're going to need it later. And then later we can use mprotect to say, I want to write a little bit of machine code here. And then afterwards, I want to mark this memory as executable. And then when we change the protection flags of those pages one at a time, then the operating system will actually map them. Another big improvement that was done by Takashi Kokubun and Alan Wu is that we've implemented code GC. So we're allocating a large chunk of memory that we fill gradually. But if we fill this region of machine code, then what do we do? Well, some machine code at some point is maybe not that useful anymore. So some IC might have been collected by the Ruby GC, and some code may never be run again. Like for example, if some code is needed while you initialize your Ruby program, maybe you'll never run that code again after initialization. So it would be kind of useful to be able to throw away this code and start JITting all over. And now with Ruby 3.2 we can. We've also spent some amount of time optimizing YJIT's metadata to make it smaller. In YJIT, the main source of metadata is context objects. Here we have antagonistic goals that pull a little bit in two different directions because we want the metadata to be as small as possible, but also as we add new optimizations to YJIT, we also want to store as much information, as detailed information as possible. So we want the context to be smaller, but we want it to store more information. So we need to represent this information very compactly, very efficiently. Using a systems programming language like Rust here is useful because we can really optimize, get the most out of those bits as possible. I found it useful while working on this to kind of work backwards from a goal. So say you have a fixed number of bytes and you want to store as much information into these bytes as possible, then you can ask the question, well, how much information can I pack into n bytes? And right now the context struct is 29 bytes. So 29 bytes is actually a lot. You can store a lot of information in 29 bytes because it's about 6.9 to the 10 to the 69. That's a lot of possible values. I won't go into the details of this. You can look at the YJIT source code if you want. But our context struct is really tightly packed. We have no pointers in there. And basically, every single field is either 1 byte or an array of just a couple of bytes. Like, for example, the types of local variables, we store the types of up to 8 local variables or up to 8 values on the temp stack. And each type is only takes 1 byte, and the whole thing is 29 bytes. So looking forward, what's next for YJIT? With Ruby 3.3, you're going to have the option of being able to start YJIT manually if you want. On benchmarks, I found that this reduces memory usage a little bit further. So you can do Ruby --YJIT pause, and then later you can call Ruby VM YJIT resume to start YJIT manually. And what this allows you to do is basically let all of your initialization code run, and then once you actually want to serve web request or you're done booting, you can actually tell YJIT, okay, I'm ready to JIT some code now. So you don't waste any time JITting anything, or you don't use any memory JITting during boot. And this is available now in Ruby Master, so you can try it and you can feel free to reach out and tell us if it's been working well for you or not. We are also going to have register allocation. Tachyon has been working hard on this. I think the most obvious benefit is in terms of allocating registers to values on the temp stack. So instead of pushing and popping values on the stack, you put them in registers. And it's going to be coming to Ruby 3.3. Another thing I would like to improve is the code that we generate for method calls right now. I think it's very inefficient, especially like this is all of the code that we generate to call the hash fetch method, which is a C function. This is the actual instructions that call the C function. So there's just a lot of overhead doing all kinds of bookkeeping, and potentially we could make that a little bit more efficient, either with metadata inlining or by designing a faster calling convention, only pushing the Ruby frames lazily or something like that. I also want to talk a little bit about profiling. I said earlier, we gather a lot of statistics for YJIT's development. I feel like we on the YJIT team, and maybe the world, doesn't do enough profiling. We have these powerful tools called profilers that can give us a lot of detailed information into what is actually taking time inside of a program. We don't use them enough, I think. Peter Drucker said you can't optimize what you don't measure. There's also maybe a corollary to that, which is you only optimize what you measure. So maybe we need to measure more things. Takeaways, we've done a lot to increase the performance and usability of YJIT for Ruby 3.2 and also for Ruby 3.3. But improving performance is not just a matter of adding more optimizations. You need to optimize the things that matter. You have a choice in what you decide to optimize. And intuition is often right, but also often wrong. So choose some good benchmarks and use a data-driven approach. There's also more to optimize than just peak execution speed. People tend to hyper-focus on speed, but warm-up time, memory usage, those are things that people care about and that make a real difference when it comes to actually deploying software in the real world. And of course, we're not done. We're optimizing many more things for Ruby 3.3. So thank you for listening. And we want your feedback. Ruby and YJIT cannot phone home. So if YJIT is working well for you or YJIT is not working well for you, well, please tell us. Like, we've seen people on Twitter claim that YJIT is performing really well. I've also seen people on Twitter claiming YJIT does not give me any performance boost. Well, if YJIT is not giving you a performance boost in your application, we'd like to hear more about your application, and maybe we can actually fix that. But of course, if YJIT does work well for you, please let us know as well. We can use some positive feedback. Thank you.